Hi, Matthew.
Hi, Faith and Gerald. How's it going?
Good. How are you?
Doing well. What do you think of online classes?
It's okay. It's really hard for me to focus most times, though.
That's fair. I feel that. If you guys like this stuff, you guys would love Chem 482. If you don't like this stuff, you're probably a normal person. All right, hello to everyone joining. One other thing I guess I wanted to point out, the original worksheet I posted on Canvas had one equation incorrect, which I believe is still here. So this should be on the second page, delta S surroundings equals negative delta H system. I did change that almost immediately afterwards, but if you were really on the ball and downloaded that immediately afterwards, you might have that equation wrong. So just something to double check. But other than that, we should be good. I guess I should probably wait. Oh no, it's 11. Okay. So we'll get started. I guess I'll start with my entropy joke. So entropy used to be one of my areas of concentration, but lately I've been spread too thin. Haha. Okay. Enough of that. If you guys could see my face, you would know that I hate these jokes as much as you do. But yeah, so we're gonna get right into the recitation then, I guess. The first thing I did want to point out was one equation on the homework assignment that I've been getting a lot of questions about. And I just kind of wanted to give you the equation you'll need to use to be able to solve that one. And I believe it was actually the second one on the homework assignment. And so basically what that question asks for is it gave you an equation that I believe was something like you have N2O, maybe two of those or something, going to, I forget exactly what it was, something like, what is it, 2N2 plus O2. And so what you need to know for this equation is when it gives you, it wants you to find delta E. Delta E is the same thing as delta U. You might see delta U if you try to look up how to do this online. They are the exact same thing. Our book just uses delta E. But either way, what delta E is going to equal is basically negative delta H, or sorry, it's positive delta H minus delta Ng times RT. And delta Ng here is the number of moles of gas. So if you look at this equation, these are all gas. I forgot to label that. But basically, delta G for this equation will be 3 moles of gas on the products minus 2 moles of gas on the reactants. So delta Ng for this problem is going to equal 1. And basically, using this equation, you'll find the molar energy in joules for 1 mole of this reaction. You'll then have to use the mass it gives you of N2O to figure out how many moles of N2O you have and use some stoichiometry to figure out what the actual delta E is for this. But I'd say the key for this is if you're looking up online, once again, delta E is the same thing as delta U. It's just different notation depending on the book. But that's the main question I've had on homework. Did anyone else have any questions regarding anything from the homework assignment? Okay, we will get started then. So I'm not going to get too far into Gibbs free energy today. I don't think that's not my plan. If we have time at the end, I do have a backup problem that's not on the worksheet that we can do. But I did want to start off with a little solubility just because that will be something that's kind of important on the exam. And so for this first one, I guess I'll kind of just see how you guys do with it. Remember how these equilibrium problems are set up, and you'll look at what the initial concentrations are and see if you can figure out what that equilibrium concentration is. I'll give you guys a few minutes to do that. Once again, if you could send me what answers you're getting as you are getting them, that would be cool just so I can kind of see where you're at. I will warn you that the value in grams is going to be a really small number, so don't be afraid if you get a really small value. Okay, so I've gotten a couple people who are unsure of where to start, and one person's gotten the right answer, but just to make sure that people are kind of on the same page, I am going to start working through this just to kind of show you what to do. So what we're going to look at is originally we were given the KSP of calcium carbonate here, and it also has calcium chloride present in the solution. When it doesn't mention a KSP for a compound, we're going to assume that it's just really soluble, so it's not going to be precipitating out at all, and we're going to assume it's actually completely broken up in solution. So what this means is currently in the solution, we actually have 0.05 molar calcium 2 plus already in the solution, as well as 0.10 molar Cl minus. And the reason this is 0.10 is there's 2 Cl minus ions for every 1 calcium chloride. So looking at this then, what you need to look into is actually what's called the common ion effect. And so if you look at the equation when calcium carbonate breaks up into a solution, you basically have calcium carbonate, which is a solid, which is going into calcium 2 plus ions, which is aqueous, plus carbonate 2 minus ions, which are also aqueous. And so what you have to think of happening for this type of equation is it's actually going to be a type of ice table. And remember, solids don't participate in the ice table, so this whole column isn't going to be used. Looking at what's going on over here then, you have calcium and carbonate that are present. Initially, we said we had 0.05 molar calcium ions in solution, as well as 0.10 molar chloride ions. Chloride ions aren't part of this reaction, so we can actually ignore them. However, we do have to worry about the calcium that's already present in the solution. So the initial concentration of calcium is just going to be 0.05 molar. Carbonate, there wasn't any other carbonate until we're adding some, so right now the concentration here will be 0. If we want to find out what concentration will actually make it so it's completely saturated, and when something is saturated, that's when something starts to precipitate, because that means it's held basically as much dissolved in that solution as possible, and it's going to start solidifying out. what we actually want to do is basically like any other ice table. We're going to actually add x and add x. The reason you know that you can add x right away is this is a similar situation where you're going to look at q compared to k. When this is 0 here, though, you instantly know that this side is going to be 0 when it looks at that. So you're going to push the reaction towards the side that has something that starts with 0. But at equilibrium, we're going to have 0.05 plus x, and x is these two concentrations. And so basically what you need to do then is just solve for x. And so remember, for any equilibrium equation, you're going to have k equals products times each other over reactants times each other. In this case, there's no reactants we need to worry about because it's a solid. So what we're going to do is just have it so KSP equals x times 0.05 plus x. And all you're going to do then is use this for KSP and plug that in your calculator. Whatever you get for x is going to be equivalent to the number of, or basically the molarity of CaCO3 you're going to be adding. So hopefully that helps start. You're going to get to molarity. Remember, x will be in concentration. So to find a mass that you need to add, you'll actually have to then do a little converting at the end. I will give you a hint that you'll need the molar mass, and I forgot to write that on the worksheet, but the molar mass equals 100.09 grams per mole. Okay. So I'll give you a few minutes to finish that one up, and you can start off the next one as well. The next one, if it's pure water, all that means is there's just going to be no initial concentrations at all for either ion. And all you'll have to do at that point then is just do an ice table with both starting at 0. The only reason I'm having you do that is so you can kind of compare how having that common ion changes the solubility. So I'll give you a few minutes to work on A and B actually. And once again, if you could send me your answers as you get them, that would be cool so I can kind of see where you're at page. So looking at this, the KSP once again was this value here that I underlined. Just didn't want to write it again because my handwriting's already not that great on this iPad. But either way, when you plug this in your calculator, you should get that your X value is actually 6.623-ish, give or take, depending on how you rounded, times 10 to the minus 8. And so looking at what that means, remember, anytime you're using an ice table, these values are all going to be in concentrations. And so because these are in concentrations, what that tells you is that this is going to be molar. The next thing you have to look at then, if we want to figure out how many grams, so this tells us that once we make calcium carbonate be 6.623 times 10 to the minus 8 molar concentration of each ion, that it's basically going to start precipitating out of solution. If we want to figure out how many moles this corresponds to and then how much mass that corresponds to, all I'm going to do is first convert molarity to moles. And remember, to do that, you just multiply by the volume. In this case, it's 1 liter, so I made it a really easy conversion for you. All that means is if you multiply by 1 liter, this gives you 6.623 times 10 to the minus 8 moles. And then all you have to do, I'm kind of running out of room here, I apologize. But what you'll do then is have 1 mole is 100.09 grams. When you multiply that out, so you'll just multiply that by 100, you're going to end up getting 6.628 or so times 10 to the minus 6 grams. And that is how much you can add to the solution before something starts precipitating. And so that's obviously a very small number. So that's why, thinking back to like last semester when we considered calcium carbonate, that would have been one of our insoluble solutions. So that means, or salts, I mean, so that means that it kind of makes sense we'd call it that, just because you can barely add anything before it's insoluble. However, you are actually able to add a little bit into the solution, a very, very small amount, like smaller than any balance can measure, but you can actually still add some because it is very slightly soluble. And so looking at the next part then, I think I'll just solve that one as well in the interest of time because a couple people did get that as I've been working this out. But basically all you're gonna do for this one, it's a little easier just because instead of having 0.05 as your initial concentration, what you're gonna have is 0 for that. So once again, the reaction is gonna be calcium carbonate, which is a solid, going into calcium 2+ ions and carbonate ions. I'm just going to write the ice part here because the calcium carbonate, once again, isn't going to actually participate in equilibrium. All you have to do for this then is if these are both 0, you're obviously going to be adding X to this. You end up getting X and X. So all you have in this case then is that KSP equals X squared. And X then is going to correspond to the concentration of each of these ions, which, since they're both 1-to-1 with the salt you're adding, once again, will basically just correspond to the number of moles of calcium carbonate you can add to the solution. So all you're going to do then, if you plug this into your calculator, I believe you get, let's see, yeah, so 5.75 times 10 to the -5 moles. And for this one, once again, the concentration is in 1 liter of solution. So this is going to equal, sorry, this was originally molarity, not moles. However, when you multiply by 1 liter, this is going to equal then 5.75 times 10 to the -5 moles. And all you're going to do then is multiply this once again by the molar mass. And so if you do 5.75 times 10 to the -5 moles times 1 mole is equal to, once again, 100.09 grams. What this is going to give you is 0.00576 grams. And so the point with this one, it maybe wasn't a great example because they're both kind of small numbers, but hopefully you can see that this value here is actually a lot bigger than this value up here. And so this is why if you dissolve something in a pure water solution, it's going to be more soluble than if there is this common ion effect, which the common ion for this is calcium. So I don't know how much you're going to have to worry about the common ion effect or pH effects or things like that on the exam. I just wanted to, I think something like this really makes sure that you understand what's actually happening in a solubility reaction. I did want to do this follow-up question really quick then for 2A. What does it mean if Q is bigger than K for solubility reactions? And so basically all that means, if Q is bigger than K, that means a precipitate is going to form. And so if I gave you a concentration to start with, and basically you need to determine whether or not a precipitate has formed so far, all you have to do is look at that Q value. If it's bigger than K, a precipitate will have formed. And so basically all I'm going to do for this then, I guess for this I'll write first. So a precipitate will form. And that's that for this part. Looking at B then, the question for this one is where you're going to kind of look at what this Q value is and determine whether or not a precipitate is going to form. I think I'm going to work this one out too with you just because it's kind of basically just going to be a new problem that you haven't seen before. And I do think it's similar enough to the other ones that you should know how to do it, but I think an example would be good. So feel free to try it on your own as well. I'm just going to kind of start working it out too. But basically all you have to do for this one is you're looking at how much of each of these is actually present in solution. So for calcium chloride, once again, so we have 50 milliliters of this that we're combining with 50 milliliters of this. The first thing I'm actually going to do is figure out how many moles of each of these there are. And so to do that, for calcium chloride, we have 50 milliliters. And then we're going to multiply that by 0.0010 moles per 1,000 milliliters. And I just did this instead of converting it to liters. This works as well. And what this is going to give you then is 5 times 10 to the minus 5th moles of calcium chloride. Looking at sodium sulfate then, it's going to be the same calculation to figure out moles. So all we're going to do for this is do, once again, 50 milliliters of this. We have 0.010 moles over 1,000 milliliters. And this is going to give you basically 5 times 10 to the minus 4th moles of sodium sulfate. And so this might have been kind of a long way to do it. You could have actually just done M1V1 equals M2V2 because you're combining these two solutions. But looking at what the new total volume is once you've combined these, you have 50 milliliters plus 50 milliliters. So the new total volume is going to be 100 milliliters. So what that means then is if you want to find the new concentrations, you'll just divide the number of moles by that number of milliliters, or by that volume, sorry, in liters. So if you divide 5 times 10 to the negative 5th moles by 100 milliliters, what that's going to give you is 0.0005 molar for this. If you divide this by 0.1 liters, that's going to give you 0.005 molar. So at this point, we found the new concentrations for each of these. And now it's actually going to be not too difficult, I hope. We're literally just going to look at what the K value equals for this. So KSP we said equals 2.4 times 10 to the minus 5th. Remember what K actually is going to equal is the equilibrium concentration or equilibrium constant for the calcium sulfate breaking up in solution. So this is going to equal then, if you think of the reaction for calcium sulfate, you have calcium sulfate in solution breaking up into calcium 2 plus sulfate 2 minus. And so what KSP is going to equal then is KSP equals the concentration of Ca2 plus times the concentration of SO4 minus. Then going back to what we learned with equilibrium earlier, you also have that same thing, but Q equals this same concentration, except you don't worry about equilibrium yet. And so all we're going to do actually is make it so Q equals the concentration of Ca2 plus we have now times the concentration of SO4 2 minus that we have now. And so all I'm going to do to look at that is look at, so if we mix these in solution, right now we have 0.0005 molar calcium chloride. Since the ratio of calcium ions to calcium chloride is 1:1, remember you know that just by the empirical formula, that means the concentration of calcium 2 plus is going to be 0.0005. The concentration of SO4 2 minus then, looking once again, SO4 has a 1:1 ratio with sodium sulfate. So for every 1 mole of this, you'll have 1 mole of the sulfate. So we're gonna have this times 0.005 molar sulfate. And so once again, right now we're just finding that Q value so we can compare it to the KSP. When you multiply these two things times each other, you end up getting that Q equals 2.5 times 10 to the minus 6. And so all you'll actually have to do for this part then is compare Q to that K value. And when you do that, you should notice that Q here is actually less than the KSP value of 2.4 times 10 to the minus 5th. And so because it's less, that actually means that no precipitate is going to form. So I'm just going to label that as no precipitate. And that actually then is kind of the answer to C as well. No precipitate's going to form here either. And I don't think you're actually going to have to worry about calculations like that for the exam. So that's kind of why I did this, but don't know why I wasted so much paper on that question, I guess. But either way, no precipitate is going to form. So the mass here is going to be 0 grams. Are there any questions on that before I move on to some of the entropy stuff? Okay. So we're going to basically completely switch gears. I can come back to this next week during review, or feel free to email me if you don't understand anything about solubility. Next week will be a little more like test review oriented, just because the test will be the following day. But moving on to entropy, before we get started, just to kind of see what you guys know about spontaneity, and for a little fun, I guess, message me a spontaneous process that you can think of. So any spontaneous process. I'll just give you a minute or so to do that. All right, so far I just have 3 answers that are ice melting. So that's not wrong, but not as exciting as I thought it would be. But oh well. I'll just give another minute or so if anyone can think of something clever. Otherwise, I'll move on. Ball rolling down a hill is another nice one. Hydrogen peroxide is good. Decomposing, yep. And getting coronavirus, another, hopefully not spontaneous, but yeah. Okay, so looking back at it though, I do want to correct one thing about the ice melting. One person did specify at room temperature, and that actually is the key for this, is that in order for it to be spontaneous, remember, the total entropy of the universe has to be what's positive. And so thinking about what's actually happening, if ice melts at room temperature, yes, it is spontaneous. Just be a little careful with that. If it's happening at some point below freezing, it's actually not going to be spontaneous. So just keep that in mind. But looking at what the definition of entropy is then, I guess this is kind of a little different, but remember, entropy is just the measure of the number of microstates in the system. So I'm going to write that here. And so basically what that means, remember, we looked into that definition of like entropy equals K, L, and W. You're not really going to have to do calculations like that too much, just because that's kind of more of an abstract way of thinking. But what you can think of as number of microstates is the number of different possibilities something can exist in. And so, for example, just to compare, we'll compare a solid, liquid, and gas in a container. If you have a solid in a container, basically remember the only motion that that solid can have is vibrational motion. Nothing's going to be rotating or translating or anything like that. So at any given instant, the number of microstates is basically kind of fixed just at those little bit of vibrational motions, but even the vibrations don't move that much. So this has like very few microstates. If you compare that to a liquid, so we'll put it in like a closed container. If we have a liquid here, this liquid then has a lot more microstates possible because at any given instant, those particles can basically move around each other. And so you could basically have at one instant, like a certain particle is on the left side and then slightly it's going to move over here. Basically, it doesn't really matter what's going on, but the particles can move around each other. Gases then have even more entropy, just because if you have gas particles in this box, they can literally fly anywhere. There's no intermolecular forces holding them in place. And so that's kind of why, if you think about what's actually happening with entropy, why as something turns into a gas, there's going to be a greater entropy, if you think about it more as that like that microstate system. And once again, if you guys are really interested in this stuff, you can take Chem 482 at some point and learn all about entropy. However, I would not recommend that class. So I would say don't take it. But if you're a chem major, you'll have to take it. So it's not that bad. But thinking about then what this question is, and I kind of did cover this already with that example earlier. I probably should have asked it a little later. Should the delta S of the universe be positive or negative for a spontaneous reaction? The answer is, of course, it should always be positive. And so what that means is that as the universe continues throughout time, slowly things are basically going to spread out as much as possible. The number of microstates is going to increase regardless. So any spontaneous process is going to increase that entropy of the universe. So then for number 5, true or false, if you guys could message me just true or false for this one, just to kind of see what you're thinking and see how much more in depth I'd have to explain this. So is the second law of thermodynamics, does it state that a spontaneous process must always have a positive enthalpy of the reaction? Okay. So I'm giving a little bit of each. So far, more false. So looking at that, okay, yeah. So if you're going to think about what's actually happening with entropy, remember the delta S of the universe is what should be positive. So thinking about what's happening then, the second law of thermodynamics is the one that states that the spontaneous process must have a positive enthalpy of the universe actually, not the reaction. And so you can kind of think about that looking at these equations to know I have down here. It's delta S of the universe that you're worried about. So this one is actually going to be false. The reason is that this term here should be enthalpy of the universe. And then so the last one, at what point is entropy equal to 0 joules per mole Kelvin? This one is just kind of thinking back about actually that third law of thermodynamics. And remember, this one is just going to be when you have a perfect pure crystalline substance at 0 Kelvin. So I'm just going to write pure crystalline substance at 0 Kelvin. And so remember, all this means is that at that point, there's literally only one microstate it can exist in, because all of the particles are fixed in place. There's no motion at 0 Kelvin in a pure crystalline substance. It's basically going to be perfect. So at that point, there's going to be no entropy. So then moving on, we're just going to do one entropy, I guess 2 entropy calculations. And then this will probably be, yeah, this will be all we'll have time for, I think, looking at what time it is right now. So looking at this reaction, the fusion of water at 0 degrees Celsius. Remember, so water is always going to fuse when the water itself is at 0 degrees Celsius, regardless of what the external temperature is. So if it's 80 degrees outside, but the water is somehow freezing. In order for that to be happening, it has to be at 0 degrees Celsius, that water itself does. So kind of just to think about what's happening when you're looking at these two equations then, if you have delta H of the system, look for both of these equations. Delta H of the system is used for both, but T of the system and T of the surroundings are both going to be potentially different. And the reason for that is the T of the system during like anything like fusion or anything, it's like evaporating or anything like that, this has to be fixed at that boiling point or melting point, whereas the temperature of the surroundings could be different. So that's where you could like compare water melting or freezing at certain temperatures. And so using these equations, see if you can figure out really quickly what the delta S of fusion is for 0.4 kilograms of water melting at 0 degrees Celsius. So remember, it could be at a different temperature, but water always has to be melting at 0 degrees Celsius. So that will be the temperature of this system. So if you guys could send me your answers for that, I'll give you a few minutes to work on that.